Brines from salars and salt lakes, as well as spodumene ores, are the primary sources of lithium, while geothermal and other brines represent secondary sources. Produced water from oil and gas operations is an untapped source of lithium that may be more important in the future. Chemical precipitation, adsorption with inorganic ion exchange sorbents, solvent extraction and concentration with membrane technologies are the primary means of lithium recovery from brines. Each lithium extraction and recovery process has unique advantages and challenges that need to be considered when determining the best fit for any project. New advances in water processing offer exciting improvements on the economics of using membrane technologies for lithium recovery. Roughly half of the world's commercial lithium is recovered by concentrating naturally occurring lithium brines in evaporation ponds. This practice is low cost and provides till 50% recovery, but is only feasible in arid climates. New technologies are enabling higher recovery of lithium from saline brines without the need for an evaporation pond, opening opportunities in non-desert geographies. What are the primary sources of lithium? Due to continuing advancements in mobile devices and electric cars, the demand for lithium is outpacing the rate at which lithium is being mined from brines. Lithium is an abundant element, but there are very few commercial resources where lithium is found in concentrations sufficient for producing useful lithium compounds. The primary sources of lithium are in brines from salars and salt lakes, and lithium-bearing spodumene ores, while geothermal brines represent the second most productive sources of lithium. Lastly, produced waters from oil and gas fields are an untapped source of lithium that may grow in importance in the future. To ensure the productivity of these lithium resources, it is essential to have lithium recovery technology and processes that are optimized to the characteristics of each individual resource, such as the concentration of lithium, the ratio of lithium to magnesium and calcium ions, and relative concentrations of other ions. Lithium recovery via chemical precipitation. Lithium recovery via conventional chemical precipitation normally starts by subjecting lithium-rich brine to a series of solar pond evaporations. This will precipitate other salts, such as sodium chloride and potassium chloride, while concentrating the lithium. Lime, calcium hydroxide, is then added to the concentrated lithium brine to further remove magnesium as magnesium hydroxide, and sulfate as calcium sulfate. Any calcium in the concentrated brine is removed as calcium carbonate by adding sodium carbonate. The brine that results from these chemical precipitations is then subjected to a carbonation process, where the lithium reacts with sodium carbonate at 80–90 degrees C to produce technical-grade lithium carbonate. This can be further purified to produce battery-grade lithium by redissolving the lithium carbonate, and then using an ion exchange process to remove impurities. To reduce the time that is required for solar evaporation concentration, lithium will sometimes be precipitated as lithium phosphate, which precipitates more quickly than lithium carbonate due to its roughly 30-fold lower solubility. Lithium phosphate is then converted into battery-grade lithium hydroxide through an electrochemical process. Lithium recovery via adsorption. Lithium selective ion exchange sorbents are a promising alternative for extracting lithium from brines. Inorganic ion exchange sorbents, such as lithium manganese oxides, spinel lithium titanium oxides, and lithium aluminum layered double hydroxide chloride, have been shown to have high capacity for selective lithium uptake. However, the recovery process requires the lithium to be in contact with these sorbents for long periods of time. Additionally, sorbents can be very expensive. They are mostly available as powders that require energy-intensive processes for lithium recovery and can degrade during the acid-driven desorption process. A novel technique based on an electrolytic cell that contains lithium iron phosphate as an electrode material has been studied to selectively recover lithium. Under an electrochemical process, lithium ions from a lithium-bearing brine are selectively intercalated into a cathode made from iron phosphate to form a lithium-saturated lithium iron phosphate. Then, the current is reversed, turning the lithium iron phosphate into an anode that can be used to recover lithium. Lithium recovery via solvent extraction. One approach that has been tested to selectively recover lithium from brine involves using an organic phase that comprises kerosene and an extractant, such as tributyl phosphate, trioctyl phosphine oxide, topo, and beta-diketone compounds. Although these organic phases show very high selectivity toward lithium over sodium and magnesium ions under optimized conditions, the lithium stripping phase uses solvent extraction that can result in costly equipment corrosion. In addition, the residual brine that remains after lithium extraction may require post-treatment to remove the leached solvent before it can safely be sent for disposal. Lithium recovery using membrane technologies. Reverse osmosis, RO, and nanofiltration, NF, processes have been studied for pre-concentrating or separating lithium from a lithium-bearing brine. A typical lithium brine usually contains high concentrations, for example 5.0 Wt%, of salt ions. The maximum salt concentration that an RO/NF process can reach is linked to the osmotic pressure, as well as the membrane selectivity and the mechanical stability of any associated equipment. Automated chemical softening systems, such as our brine refine system, can help membrane treatment systems reliably reach their treatment limits and improve yield. Conventional NF processes cannot efficiently separate lithium without heavy pre-treatment of the brine, such as diluting the brine with a large amount of fresh water. Electrodialysis systems, such as our Flex EDR Selective, should be viewed primarily as concentrators and not as refining technology. This is because today's monovalent EDR systems cannot separate sodium from lithium, and although monovalent electrodialysis may separate monovalent ions from divalent ions, the separation is less effective than chemical methods in the case of lithium, resulting in higher yield losses. Seawater contains significantly larger quantities of lithium than is found on land, thereby providing an almost unlimited resource of lithium for meeting the rapid growth in demand for lithium batteries. However, lithium extraction from seawater is exceptionally challenging because of its low concentration, from 0.1 to 0.2 parts per million, and an abundance of interfering ions. Herein, we creatively employed a solid-state electrolyte membrane, and design a continuous electrically driven membrane process, which successfully enriches lithium from seawater samples of the Red Sea by 43,000 times, i.e., from 0.21 to 9013.43 parts per million, with a nominal Li/mg selectivity greater than 45 million. Lithium phosphate with a purity of 99.94% was precipitated directly from the enriched solution, thereby meeting the purity requirements for application in the lithium battery industry. Furthermore, a preliminary economic analysis shows that the process can be made profitable when coupled with the chlor-alkali industry.